Welcome back to as we continue to study differential equations. And this, I believe, will be the last of the videos on differential equations, and thus the last lecture of we refer to as the regular season before we go into our review for the calculus AB test. One more topic I really want to cover, L'Hopital's rule, but I'm going to cover that during our review when we get back to limits, because it's not a topic of AB calculus, but it's just so useful and handy that I will teach it to you. But anyway, back to this. So if there's any motivation, this is the last one. That's basically what I'm telling you. Here we're back to solving difficult Diffy Q's continued. Remember the last thing we looked at? First of all, I showed you how to solve separable differential equations, how to come up with an algebraic solution. But then I showed you a problem last time where you couldn't find an algebraic solution. You couldn't separate it. So we drew little tangent lines in an XY field, and then we carefully drew a solution curve through that field of slopes. Okay, so that we used the tangents, the little tangents, as little guideposts to draw our solution curve through. Well, let's see what's tough about this problem. I say here we're going to use the fundamental theorem. We're back to the fundamental theorem. First thing we do here, though, we got a differential equation, right? We got a derivative. We got an equal sign. The differential equation is equal to that. We also have a point on the solution curve. We're trying to find the solution. We're trying to find what the function y is. What's our first thing? Well, we separate. We say dy is equal to e to the minus x squared dx. Next step, right, we're going to integrate both sides. Integrate the left side, I get y is equal to e to the minus x squared dx. Well, how do we integrate that? Well, you probably would try to do something here. Do you see substitution? I don't see substitution. Is this one you know? No. You might try. I know in the heat of battle you might say, oh, this is probably just e to the minus x squared over minus 2x. And that would be wrong. If you take the derivative of that, you won't get this. So in reality, what makes this difficult is you can't integrate this. In fact, in order to integrate this function, you need a Taylor series, something out of BC calculus. So you can't integrate it. Well, what can you do? Well, I can kind of leave it like that, right? I'm going to leave it like that, and I'm going to say, well, and I'll just write something down here. I'm going to integrate this from 2 to x. Okay, so I'm going to say y. I don't have an explicit algebraic expression, but I'm just going to say it's equal to the integral of this. Now let's test it. Does it work? What is dy dx? Well, dy dx is just equal to, remember the fundamental theorem? That's just going to be equal to e to the minus x squared. Okay. Well, let's see. This checks. What about this? How do I make that? Well, what is y at 2? Remember, this is kind of saying y at x is equal to 2 to x e to the minus x squared dx. All right? What is 2? If I put in 2 here, that's 0. But y of 2 is not equal to 0. It's equal to 7. So what do? I add 7, not inside the integral, outside the integral. Okay. Now look at this. So there's your answer. In general, your answer. Again, well, let's test it. Let's see if it works. I mean, if it works, if it works, let's switch colors. It needs to satisfy this. We've just shown it does, but let's just show it again. Let's show it again. Well, what's dy dx? dy dx is equal to e to the minus x squared. What is y evaluated at 2? Y evaluated at 2, I put a 2 in here, it's equal to 7. Check, check. That's my solution, right? That's my solution. It's always going to work. Now, the thing is, I can use my calculator, for instance. I can use my calculator and I can tell you, the question might ask you like, okay, tell me what find what y of 3 is equal to. Well, y of 3 is just going to be 2 to 3 e to the minus x squared dx plus 7. Okay? So, I haven't integrated here, but I actually do have a solution. I write my solution as an integral equation. Pretty slick, huh? Next thing we'll do, let me just show you in general what happens. In general, whoops, write this up again. Let's say I get dy dx as some function of x. Has to be a function of x. And then I give you a point. I'm given a point on the curve. Y is equal, at a, the function is equal to y. Okay? So I get a point on the curve. What's my solution in general? Well, I should kind of write it. I put this function down here, t. I start it at a. I can put an x up here. I say y is a function of x. Notice this x goes here. So this guarantees that the derivative of y with respect to x is going to equal f of x. And now I add f of a. Okay, so notice I start my integral where I know the function. And then I add it, okay? In general, this is my solution and will always work. Okay, I'm going to go try to find a problem. I'll put it up here. We'll work a homework problem. Okay, here we got a problem here. We got a differential equation, right? du dx is equal to the square root of 2 plus cosine. And here we're given a point on the curve. Okay, we try to separate this thing. Okay, we start to integrate it and we'd find out we got problems. Okay, I do not know how to integrate the square root of 2 plus the cosine of x, but I could say u is equal to the integral of the square root of 2 plus the cosine of x. If I want a function of x here, I could make this an x. And I'm going to integrate it from where? Well, I'm going to integrate it from where I know it, at x equal to 0, x equal to 0, up to x. Typically what we do is we change the variable here. This confuses people, but I'm going to do it anyway. I'm going to make this a t here. This doesn't change the problem at all, right? I put in a t, and I'm going to integrate from x. If I put in a 0 here, if I integrate from 0 to 0, that's 0. But I know at x equal to 0, u is equal to 3. So I do my minus 3. Remember my last bit, I say I'm going to start integrating from where I know the function and then add that. So that, whoops, undo that. Here is my answer. Okay, now let's try something here. Find the function. Find what u of 5 is equal to. U of 5 equal to. I'll stop the video. Let's go to our calculators and see if you can get the right answer. Okay, I went out to my trusty old TI calculator. I'm going to make sure I'm in radian mode. I'm integrating from 0 to 5, right? That 5 goes in here. Square root of 2 plus the cosine of, I could put it in as x here, t dx. When I did that in my calculator, I got that was equal to 6.6126. Okay. Now I'm going to subtract 3 from that. Subtract 3 from that. I'm going to get 3.613. That would be my answer. Let's make sure I'm in radian mode. Sure enough. Okay, so again, what have we done here in this video? Let's go back. Here we've got a difficult differential equation. I can separate it. Easy to separate, but I can't integrate. So I set up an integral equation in order to solve it. This will always work, by the way. It'll work even if you know how to integrate this, right? If this function was e to the minus x, you could still integrate it. Okay? And this equation would work, but maybe the question would want you to give a closed form algebraic expression. But in general, if you're given an equation that looks like this, whether you can integrate it or not, you can come up with an answer that looks like answer 1. I'd suggest you just use this, though, when you can't find the antiderivative of this function. Okay, well, that does it. That's the end of differential equations, the end of the regular season. I look forward to getting the regular season going shortly. See you soon. Bye-bye. Bye.